Good morning, good afternoon, good evening, wherever you may be in this part of the world, and welcome to another session of my presentation series. And this time, the topic is application of machine learning algorithm for fault detection, distinguishing, and classification. And it's applicable to any industry that is in the world. My good name is John Kweku. I'm Otu, and I've been an electrical engineer for the past 31 years, and I'm based in the United States of America. Below this is basically my YouTube channel that you can access and has a lot of tutorial technical presentations that you can use to leverage on your continuing education. And also at the end of my session, if you like my presentation, you can select the like button, and also don't you can share it, and also you can use select this one to subscribe to my YouTube channel. Next is my outline for my presentation, and the first item it's basically a definition and description of what a machine learning is, and we'll take a deep dive into applications of machine learning, which areas of industries, just to mention a few on the slide where machine learning can be applied. Next is machine learning flowcharts, all the processes that are part of the machine learning to achieve from the input to the output. Next is data pre-processing, how we pre-process the data to make it acceptable for machine learning to process the data and train the data and test the data to achieve a predictable output. Next is a typical exercise where basically, I have faulted states data and non-faulted states data, and basically I will use machine learning to distinguish between these two statuses. And the last but not the least is a fault classification, where basically I will use a machine learning algorithm to distinguish between the two faulted states based on different categories of faults. Next slide is what's machine learning, and that is the buzzword that has been going around for the past 2 years, right after COVID. Matter of fact, during the unprecedented COVID time, that is when machine learning started skyrocketing. Okay, so this is the definition. Machine learning is an implementation of artificial intelligence. Okay, so artificial intelligence has been around for some time, right? But machine learning just evolved out of artificial learning, right? So it's a branch that just evolved on its own. And a relatively new form of computer programming. Yes, it is new. And basically, what it does is it allows you to access, pre-process huge data, right? And be able to pre-process the data, have the data learn, and out of the learning, select a sample to be trained to be able to predict classification based on pattern recognition. Right? This is the right word. Pattern recognition. Okay. So now let's talk about what is happening in the fourth industrial revolution era. As you know, we are currently in the fourth industrial revolution era, right? Okay, so as part of the fourth industrial revolution, right, we already have artificial intelligence that has been hovering around for more than a decade, right? Okay, so out of artificial intelligence, machine learning just evolved. Deep learning evolved. Reinforced learning also evolved. Okay. So, as part of all this algorithm, right, that are so important for the fourth industrial revolution that we are currently in, it combines it with cloud computing, advanced data analytics, to be able to diagnose and also predict based on pattern recognition. Okay, so once we evolve from the fourth industrial revolution, we're going to go to the fifth industrial revolution, then sixth onwards, right? Okay. As we evolve or we shift a paradigm from the fourth industrial revolution to the fifth industrial revolution, right? We'll still have machine learning, but we will have much more faster algorithm, right? We'll still have a deep learning, but faster algorithms. We'll still have a reinforced learning, but faster algorithms, right? Then artificial intelligence is still going to be there, but faster algorithms, right? Okay. And robotics is going to come in, right? Here, robotics is there, right? But robotics is still evolve, it's still, growing, right? But during the fifth industrial revolution, it's purely going to be robotics that is going to dominate. Then, for your computer analytics, right, it's going to be very advanced, faster, right? Then, much faster diagnosis and even much faster prediction in nanoseconds, right? Microseconds prediction. Now let's talk about applications of machine learning. Very, very important. Like I made mention on my first slide, right? Machine learning is applicable to any industry in the world that you can think of. Right? Okay, so the first one is a search engine, internet search engine, right? Okay, so when you click on Google, right? Google app, right? And you type in on the drop down window any item that you want to search, right? So the Google app basically retains your data based on the search, right? So every day or every time that you input a search in that drop down window, what the Google app does or the algorithm does is basically it keeps that data and basically trace it and be able to predict. So that is how you see all those ads on your computer. Yes, because Google also based on your basically what it is doing is it is learning your behavior and also likes and dislikes, then be able to send you ads. So that's how Google makes its money. Next is social media, right? Social media, we have Facebook, Snapchat, WhatsApp, right? Okay. So anything that you do on Facebook, on these social media platforms, right? The algorithm stores the data and be able to learn, train its algorithms to be able to predict. Right? So that's how you see all those ads on Facebook on your page, right? Because they also sell that data and make money. It is applicable to all engineering discipline in the world, any industry that in the world. Machine learning is basically the dominating algorithm technology, right? And it is going to evolve for the next decades. The telecommunication industry, language processing, right? If you want to learn basically a new language, let's say you speak into your cell phone or your computer, right? For it to basically interpret. Let's say you want to convert English language to Portuguese or Italian or German, right? It uses machine learning algorithms. The financial markets, stocks, right? the housing industry, construction industry, the agriculture industry, medical diagnosis, right? It basically keeps all data in the past for, let's say, 50 years and be able to test the data, to be able to predict and give you diagnosis. In addition to the human review, the doctors themselves are also come up with their own diagnosis, then compare it with the computer diagnosis. Next is its use in the economics industry, economic industry. Next is a global positioning system, right? The GPS that you have. The gaming industry, predicting win or loss. The marketing, sales industry, yeah, that's how they collect the data, your search engines, right? That's how they collect the data and basically be able to market products to you. The oil and gas industry, right? The transportation industry, the shipping industry, the heavy trucking industry, the air transport industry. So, if you look at all this myriad spaghetti of industries out there that are all utilizing, will continue to utilize machine learning. So, that itself tells you the very importance of machine learning. And machine learning has come to stay. Now, let's walk through a flowchart of machine learning for classification. Okay, so if this is the algorithm, machine learning, okay, we have the supervised and unsupervised learning algorithm, right? Okay, so the supervised learning algorithm, you have to develop the predictive model based on the input and the output. You have to assign the prediction. On the other hand, the unsupervised learning just basically groups and interpret the data based on the input that you provide. Okay, so I've indicated that machine learning can be grouped into supervised learning and unsupervised learning. Okay, so now let's talk about supervised learning. And under supervised learning, we have the classification learning arm, learner arm, and regression. Okay, so under classification learner arm, we have a fine decision tree, KNN, and fine Gaussian support vector machines, algorithm classifiers, classifier algorithms. That you can utilize. Now let's pivot on regression, right? Okay, under regression, which is also a supervised learning, we have artificial neural networks. We have decision trees. We have linear regression. Now let's talk about unsupervised. Remember, I indicated that unsupervised, you provide their input data and you allow the algorithm to interpret the data based on what you input, right? So under unsupervised, we also have a cluster neural networks. Okay, so now let's talk about machine learning for classification, right? And an example of a supervised learning algorithm that I'm taking as an example, right? And that is basically the example that will be all through this presentation, right? Okay, so I have a fault data, right? Okay, so let me explain to you where the fault data is coming from, right? Okay, so I have a wind farm, right? Then on this side is a rectifier converter, MMC rectifier converter, right? That basically converts my AC voltage and current to a DC equivalent, right? Okay, so I have positive here, negative. for the DC transmission section, right? Okay, then it goes to an offshore converter, another converter, MMC converter, that basically inverts. So this is an inverter, this is a rectifier, and inverts the DC to an AC equivalent, and from there it is integrated to an AC grid. Okay. So on the DC transmission cable, that is a subsea cable, right? I applied a pole to ground faults and a pole to pole fault at various distances along the entire length of the DC transmission cable with various varying fault resistance, right? Okay. So when I performed, I basically modeled it in PS Card, our software platform, and after the simulation and performance of the faults, I collected the data, and I'll show you where the formats of the data. Right. So this is my data that I have it for pole to ground fault and pole to pole fault with varying resistance. And the example that I use is 50 ohm arcing resistance. That is when you have a fault, right? The resistance of the arc to ground is 50 ohms. So the first thing I did was pre-process the data, right? Okay, so pre-processing the data are assigning all the variables and predictors, right? And classification, right? And transform the data in a machine learning format, right? Okay, so if you do that, then basically, like I indicated, that's when you select the input predictor and the output classification. Okay, so then the next stage is to partition the data, right? You have your data, let's say 100 data points, right? Okay, so you partition the data 95% of it. So 95 out of 100 becomes your training data. Or you can select 90. You can select 80%, whichever you feel comfortable, right? So let's take, for example, you select 90 as your training data, right? Then your testing data becomes 10, right? So your training data is 90%, and your testing data becomes 10%. Then you select your algorithm, your classification learner algorithm, right? Okay, so for this example, I basically indicated find decision tree as an algorithm to be used, then find KNN, then find Gaussian support vector machine as classifier algorithms. There are many more, tons, so more than 20 to 30 algorithms out there that you can utilize. But I selected these as an example to use. And matter of fact, if you are going to do your classification learning processing, if you know of an algorithm that has a very higher performance, you can basically pre-select that. Then, based on your classification, right, you come up with the best classifier algorithm based on the highest accuracy percentage-wise, right? Then the training time. Remember, training time is very important, right? Because that basically translates into computational burden, right? As much as you want to scale back on the computational burden, and if you scale back on the computational burden, basically you are reducing cost and performance is improved, right? Okay, so and also your prediction speed, right? Very, very important, how fast you can predict. So these are the three criteria that you use to select the best classifier algorithm. Also, there are optimizer algorithms. If let's say you do your first simulation classification, and if you feel there's the need to optimize it, there are optimizing algorithms that is out there that you can also select under each classifier algorithm that will improve your percentage accuracy, your training time, and your prediction speed. Also, there's another, optimization cost, right? Okay, so if you increase the cost, right, if there's a point that has been misclassified here, right, then you can bring it closer to your hyperplane, right? Okay, so that will improve your percentage, right? Okay. Then the next thing is, you perform the testing of the data, right? Okay, so the testing of the data, let's say if it is 10%, then from there, based on the accuracy and cost, right, you get your classification in a confusion matrix, right? In a matrix format that basically indicates actual on the vertical axis of the matrix and prediction, right? So actual is your actual data, and prediction is basically your goal is to predict, to match the actual, right? So that's where you get your percentage accuracy from. So now let's talk about fault classification using machine learning algorithm. Remember, I made mention that the example that I'm going to use is a typical pole-to-pole fault and pole-to-ground fault in an HVDC, high voltage DC transmission platform that I performed the simulation in a PSCAD software platform to obtain the data for pole-to-pole ground fault, a pole-to-pole fault, and pole-to-ground fault. And these are the classifier algorithm that I am using. Okay, so this is basically the data, right? Okay, so the first one is pole to pole fault data, right? And this one is a pole to ground data, right? Okay, so pole to pole means that the positive pole and the negative pole basically shorted together, right? And basically, that's the short circuit currents are extremely high, and the voltage is equal to 0. And a pole to ground fault means that the positive pole is shorted to ground, and basically the negative pole experiences very high voltages, pole close to the pole to pole voltage. Okay, so but comparably, the fault current, the pole to pole has a higher fault current than the pole to ground. Okay, so as you can see over here, right? Okay, right here, right at the onset of the fault. Look at for the pole to pole, 9.37 kiloamps, right? And for the pole to ground, 4.68 kiloamps. So that tells you the difference between the pole to pole fault giving you your highest fault current compared to a pole to ground fault. The difference is, for the pole to ground fault, the healthy pole experiences a higher voltage, let's say 1.6 to about 1.7, the pole to ground voltage. Okay, so this basically on this axis on the left side is your pole to ground data, right? Okay, so this becomes an input to your classifier algorithm, right? Okay, so these are your variables, right? Time and the fault current. And this is your classification, right? So that is why they call it a supervised learning, right? You are assigning the classification to your data. So you have to manually go through each and basically assign this classification to your data. On the right hand side is your pole to ground fault, right? So I have my input data, right? Time, fault current, variables, right? And my prediction classification, right, is pole to ground fault for all this data, right? About 440 data points, 440 data points for this. So this will be my input into my classification learner algorithm. So in Matlab, what you have to do is have a Matlab software downloaded on your computer, right? And there are basically monthly usage that you can use for trial basis, right? So you can download it on, for 1 month to learn how to use Matlab, right? Okay, so within Matlab software platform, right, you can basically install their classification learner app under install app, right? Under install app. This is also another learner app, regression, that you can also install if you want to learn regression, right? Okay, these are all basically statistical, tools that you can use. So once you install the classification learner app successfully, this is what you're gonna see in the app section of your Matlab software. So this is Matlab 2022 B, right? Okay, so that was the last 6 months of 2022 year. They haven't come up with the newest release for 2023 yet. So I'm pretty much sure when they come up with the new one for 2023, it's going to be 2023A. So that's how it goes. So next thing you want to do is click on your classification learner app on the previous slide that I showed you, the one that you downloaded successfully from your app window, right? Okay, so once you select it or highlight it or click on it, this is the window that is going to appear, right? And it's going to show classification learner, right? So on this side is a new session, right? Okay, so you click on new session, then you see a drop down window that basically will give you the latitude, the flexibility to select the data from wherever you have your data stored. Remember the data, right? I indicated, my fault data for pole to pole fault, pole to ground fault, right? You can also, and this is applicable to electrical engineering, right? HVDC transmission system, right? It can, if you have a fault, a data that is in your industry, right, where you have your data that is faulted, right, then broken down in different categories, right? This is where the data you need. Then you have a data that is the healthy data, right? In my situation, my healthy data is steady state operation, right? Non-faulted state. So you should have a data that is faulted states, and the faulted states can be broken down into different categories, close to, I've seen close to about 10 categories. For instance, in the AC industry, right? AC fault, right? I can have a single line to ground fault, double line to ground fault, three-phase fault, right? Line to line faults, right? 1, 2, 3, 4. 4 faults, right? Okay, so the same thing in the DC HVDC industry. I have a pole to ground fault, pole to pole fault. So it's very applicable to whatever industry that you have. You can have different conditions of faults that you have and you want to process. Your steady state, your non-faulted state, is your state that does not have a fault. Okay, so this is where my data is stored, right? Okay, so I have a data that I have integrated my steady state. It's a combination of faulted states plus non-faulted state, right? So my steady state operation of the HVDC transmission network is steady state, where I don't have a fault, and faulted state, where I have a fault, right? Okay. Then my second data is when I have a fault, but I have different categories of faults, where I have pole to ground fault or pole to pole fault, right? And within that, like I told you, you can have as many as let's say 10 to 20 different faults, right? Because even within the pole to pole fault, I have a pole to ground fault at different sections, different distances, right? 0 kilometers, 30 kilometers, 175 kilometers, 112 kilometers, 150 kilometers with various varying resistance, right? 0 ohms, 5 ohms, 20 ohms, 50 ohms, 100 ohms. Let's say you can go all the way up to 1,000 ohms, right? So these are the very different faulted conditions that you can have that you can utilize the machine learning classifier algorithm to classify successfully. So you go to this folder and you select your data that you want to classify. Okay, so now once you select the data from your folder that you have on your computer, right? Okay, so this is what you're gonna see, right? As you can see over here, nicely, this is my time, right? This is my fault currents, and this is my classification, prediction. So the next thing I do is select import. Right. So once I select import, then basically I go to the next slide. Okay, so now the data center format. Okay, so this is where my classifier learner app basically processes it in the format that the classifier learner algorithm will understand. Right? Okay, so if let's say you have a total data of 100%, right? Okay, so this one I have a total data of 114, right? Okay, so out of that, I want to train 90% or 95% and set aside 5% of the data for my training sets, my testing set. This is for training and this is for testing. So I select this box, right? So that will be able to set aside 5% of my data for me to use it as a testing data. You can basically, you have the latitude or flexibility to basically, change this percentage. You can take it to 10%, whatever, based, you see, it's all based on the amount of data, right? Okay, so for instance, if I have a data of 10, 14, definitely, I would like to take only 5%, right? Which corresponds to about 50, right? Okay. If I have a data, let's say about 10,000, right? Then I'll be leaning on about 2% or 1%, right? So that's how it goes. The higher your data set, the lower percentage you want to set aside for your testing. Okay, so on the previous slide, I showed you, your data that has been processed in a format to be understood by classifier learner algorithm. Then you select the start button that is shown on the previous slide, right? Okay, so once you select the start button, then this window is going to come up, right? Okay, so over here are all your algorithms. There's a drop-down window over here, right? Once you select this drop-down window, you'll see all the algorithms, right? That I indicated. Find decision tree. Even the find decision tree is being basically broken down into different algorithms, right? Then find KNN, we have different algorithms under that. Then find Gaussian support vector machines. Under that too, we have a different many, if you select out this drop down, you see many that you have. Then what you do is you select all quick to train or select this one, whichever you go, right? Then under that, you select the one that you want. So I went ahead and selected define tree and find KNN or find decision tree or find KNN and all SVM support vector machine. So once you select that, I selected all this algorithm for my example, right? But like I indicated, you can select whichever algorithm that you feel will give you the best performance, right? Okay. Then you select train all, this one. So once you select that, then you see down here it will start populating. Now it will start processing and start giving you all the data, your output that you need. Okay, and that is what you're seeing from here, right? You have your output, right? Starting to populate, right? Okay, you have your confusion matrix, your summary over here. Then basically, your confusion matrix for your training, right? Your confusion matrix are in different categories, right? Okay, so we have the true positive rate, TPR, the false positive rate, FPR, FNR, then your positive predicted value, right, PPV, and the false discovery rate. Right? Those are all the categories that your confusion matrix will provide to you, and we'll see examples of that. So now, let's take a look at the training classification um, algorithms that we have, right? Okay, so like I indicated, let's take a look at the find decision tree, right? Okay, so for the find decision tree, we'll take a look at the scatter diagram, right? And I'll show you what a scatter diagram looks like, and also take a look at what the confusion matrix looks like, the individual components of the confusion matrix. Next is a confusion matrix, right? Okay, so I will go through, what the confusion matrix looks like, and basically you can understand what it means, right? Okay, so my total training sample is 1012, right? Okay, and my pole classification, what I'm trying to classify is a pole-to-pole fault at 0 kilometers and 50 ohms, and a pole-to-ground fault at 0 kilometers on the DC transmission line or cable, right, with a fault resistance of 50 ohms, utilizing these three classification algorithms, right? Okay, so these are my training times, and I explained to you, and my training, my accuracy. Okay, so now let's take a look at the confusion matrix, right? Okay, so the confusion matrix are basically your positive classification, your accurate classification are the ones that are on the diagonal, right? So as you can see over here, for a pole to ground fault, right, I have the true class, right? That is the actual data. And this is my prediction. This is what I want to achieve. I want to predict accurately, right? So for a pole to ground fault, right, I was able to predict accurately 467 data out of the total of this. So 467 over 467 plus 16. So that's how we get this percentage from for the different algorithms, right? So for this one is for the fine tree algorithm, as you can see over here. That's how we're able to get that percentage. 467 over 467 plus 16. Right. Okay. On the other hand, 16 of the pole to ground fault were wrongly misclassified as pole to pole fault. So that's what this means. It means that 16 out of the total of 467 plus 16 were misclassified. The same applies to this one. For a pole-to-pole fault, right? 14 out of the pole-to-pole fault data were misclassified as a pole-to-ground fault. And 467 of the pole-to-pole fault were correctly classified as pole-to-pole fault. Right? So this is how the percentages come into play. Okay, so now let's take a look at the confusion matrix, right? Okay, so as you can see, this is the confusion matrix on this vertical axis of the matrix is your true class, right? So the true class is actually your actual data, right? Then on the horizontal axis is your predicted class. That is what you want to achieve, right? Okay, so percentage-wise, basically, it is saying that for a pole to ground fault, that was the percentage-wise that was classified as correctly as a pole to ground fault. The percentage is 97.1, and the ones that were misclassified is 3.3%. And for pole to pole fault, 2.9% was misclassified, and 96.7% was correctly classified, right? Okay, so basically the percentages that you see over here, it's the overall combination of all the percentages, and there's a formula for that. Now let's take a look at the fine K-NN algorithm, right? We'll take a look at the scatter diagram and the confusion matrix, similarly just like the fine decision tree, right? Okay, so for the fine K-NN classifier, right? This is the scatter diagram, right? Okay, so as you can see over here, basically, you can see some accuracy, much more accuracy in it. You know, as from here, we don't see any classification in it. Next is the confusion matrix for the fine K-NN, right? Okay, so as you can see over here, right? Okay, like I indicated, this is basically your true class, right? Your actual data, and this is your predicted, you know, what you want to achieve based on prediction, right? Okay, so it's saying that out of the data, right, for a pole to ground fault, 473 was classified accurately for a pole to ground fault, right? Was predicted accurately, right? Then 10 of it, of the pole to ground fault data was misclassified, was predicted wrongly as pole to pole fault. On the other hand, for the pole to pole fault, 11 of the fault data that belongs to pole to pole fault was misclassified as pole to ground fault. And at the same time, 417 of the pole to pole fault was correctly classified as a pole to pole fault. Next slide basically gives you the percentages, right? Okay, so what it's telling you, it's like like the previous slide. This is your actual data, percentage-wise, then your predicted data, right? So percentage-wise, it is telling you that 97.9% of the fault data for the pole to ground fault was predicted or classified accurately, right? And 2.1% of the fault data for the pole to ground fault was misclassified as a pole to pole fault. And 2.3% of the pole to pole fault data were misclassified as a pole to ground, and 97.7% were correctly classified as a pole to pole fault. So the same, it's the same confusion matrix, and basically, this tells us basically the PPV is basically the same as this percentage over here, right? And FDR is basically your misclassification. So this one is a true classification, right? Positive classification, right? And this one is the false discovery rate. That is your misclassification. Now let's take a look at the defined Gaussian support vector machine, right? We'll take a look at the scatter diagram and the confusion matrix for the defined Gaussian support vector machine. Okay, so this one is the scatter diagram, right? Okay, so that shows basically the clear distinction. As you can see over here, this is where, basically you can see some crossing, right? Okay, so this is where the misclassification comes about, right? Okay, so that is why you see the drop in percentage from 100% to this values, but extremely, very high accuracy, right? 96.9, overall, that shows so basically this shows you your training sample and basically your fault classification and the algorithms that are using. Okay, so for the confusion matrix, right? Okay, for the fine Gaussian support vector machine, right? Okay, so for a pole to ground fault, right? 482 were classified accurately, predicted accurately, right? 482, and only one was misclassified as one data out of the pole to ground fault was misclassified as a pole to pole fault. For the pole to pole fault data, right? Okay, 26 of them were misclassified as a pole to ground fault, and 455 was classified correctly, predicted correctly as a pole to pole fault. Next slide basically shows you that your percentage works. Okay, so the previous slide gives us the actual numbers, right? But this one is converted into percentage. So for a pole to ground fault that was predicted, classified accurately, is 99.8%, right? As you can see, and this classification is about 0.2%. And for a pole to pole fault, misclassified data was 5.4%, and correctly classified data was 94.6%. So this data, is quite similar to what was on the previous slide, but it also gives us an extra data in a positive predicted values and in a false discovery rate. The positive predicted values is also the same as this percentages, right? Okay, the positive, the true positive rate, and the false discovery rate is the true negative rate, this percentages that you see over here. Now we'll take a look at the testing classification, right? Okay, so we'll talk about the fine decision tree. Okay, so now we've been able to train our data, right? Utilizing all the pre algorithms that are out there, right? Okay, so out of that testing data, remember we set aside a small percentage of it. So 5% of it out of the 1,012 data points, and basically we're going to use it as our data for testing. Okay, so for testing, right? Okay, so we have a testing sample of 50. Remember, it's about 5%, right? Of 1,012, right? So for the testing accuracy, right? I was able to achieve 100%, right? For the fine tree, fine KNN, and fine Gaussian was 98%, right? Okay, and the prediction speed is also another criteria, right? Very, 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 very important, right? Okay, so as you can see over here, right? For the fine decision tree, right? It's giving us 100% accuracy, testing accuracy, right? And look at the number of objects per second prediction, very high, right? So that itself, basically plays into the list of criteria for you to select the best algorithm, right? Okay, so what is telling us basically for testing, right? Okay, so pole to ground fault, right? 96% of it was correctly classified as pole to ground fault, right? Then 4% was misclassified. Then for pole to pole fault, 100% was correctly classified as pole-to-pole fault. Okay, so the percentages that you saw over there are basically what has been rolled over here, but basically the positive, predictive values are basically, same percentages, and false discovery rate are basically your misclassified percentages. Next is the testing classification for the fine K&N algorithm, right? Okay, so we'll take a look at we'll take a look at the confusion matrix for the fine K&N. Okay, so we have a total data of 50, right? Okay, so as you can see over here, right? So out of the 50, right, pole to ground fault, 25 of them were correctly classified, right? Then for a pole-to-pole fault, 25 of them were correctly classified. So that is why you are seeing this 100% accuracy for this fine K&N algorithm, right? Okay, so one of the things too you have to take into account is your prediction speed for your data, right? Okay, so the previous slide is basically the quantity, right, in numbers, right? Okay, this slide is giving us the percentage-wise, okay? So we have 100% pole to ground fault were basically tested and classified accurate, testing accuracy of 100%, and a pole to pole fault of 100% accuracy. Then similar confusion matrix, but in a different category, right? Okay, so as you can see over here, your positive predictive values are basically is your correct classification, and false discovery rate is your misclassification. So as you can see, misclassification for false discovery is 0 for all this. And the last testing classification algorithm is fine Gaussian support vector machine. So let's take a look at the confusion matrix for that. So as you can see here, also out of the 50 testing data, right, 25 was correctly classified, right? Okay, so out of the 50, we have 25 pole to ground fault and 25 pole to pole data points, right? Okay, so out of the 25, 25 was correctly classified, so 0 was misclassified. Then for the pole to pole fault, 1 was misclassified and 24 was classified correctly. So that is translated into the high percentages that you see for this accuracy class. And remember, I made mention that the most important is basically your prediction speed, right, for that data, right? As you can see over here, 24,000 objects per second. That is very high, right? Okay, so that itself helps us to lean on either fine tree or fine K&N as the best classifier about it. Next is basically your quantity in numbers, converted into percentage wise, right? Okay, so for pole to ground fault is 100%, right? Classified correctly, and pole fault 4% misclassified and 96% classified correctly for your testing data. Next is basically another confusion matrix, basically in a different dimension, and basically your positive predictive values, right? It's basically talking about your correct classification or correct prediction, and false discovery rate is your misclassification. So once you are able to basically do the testing for 50 samples, right? The next is basically to derive our prediction Matlab script and code, right? Okay, so I'll show you and basically utilize that code to basically predict another testing data, a green testing data that you have it prep. So basically what you do is on your classification learner app, you export this trained model into your Matlab window, right? Okay, so once you export it, it will basically come here. Then also it will ask you, there's section where you can generate your code, right? Generate code, where it will export this Matlab scripts into your Matlab window. Okay, so basically, what it's asking you is every area that you have a T2 for your new data, that's where you put the name of your new data that you want to predict based on your trained data, right? So that's how we utilize this to do prediction for new data. Next, we'll take a look at basically distinguishing between a faulted state and non-faulted state, right? Utilizing the same algorithms, right? Find decision tree, find KNN, and find Gaussian support vector machines, right? Okay, just like we used the same algorithms in the previous, basically distinguishing between different faulted states, right? But this time we are distinguishing between a faulted state and a non-faulted state. So for my non-faulted state, that is my steady state operation, no fault. Let's take a look at the training classification, right? Okay, so we'll take a look at the find decision tree, and we'll take a look at the scatter diagram and the confusion matrix. Okay, so we have a faulted state right here, pole to pole faults current, right? At 0 kilometers, right at the terminal of the HVDC converter, MMC converter, and the fault arcing resistance is 50 ohms, right? And the same as pole to ground fault at the same location and same arcing resistance, right? Okay. Then we've added the non-faulted state, right? And that is the steady state operation. Okay, so our goal is basically to distinguish between a faulted state and a non-faulted state, right? Okay, so we have a total training samples of 1,390, right? Okay, so based on the training, right, we're able to achieve a training accuracy of 98.1 for find decision tree and find KNN 98.8%, and find Gaussian 97.8%. So as you can see over here, find KNN gives us a little bit of a higher accuracy on that. But look at the training time, right? Okay, remember, I indicated that, those are some of the criteria that you use to analyze and select your best classification algorithm, because the higher your training time, that itself translates into basically, computational burden, higher computational burden, and also cost, and also basically can compromise reliability, especially utilizing this and deploying this algorithm in a device, right? Okay, so look at the training time that you have over here, right? Comparably, right? As you can see, the find tree has a smaller training time, so that itself makes us to lean on it, as a candidate to be selected for as a classifier algorithm. Okay, so now let's take a look at the scatter diagram, right? Okay, so as you can see, these are all misclassified, right? Okay. Okay, so remember I made mention, something about cost, right? Okay, so cost penalty. Cost penalty is a sign, right? Okay, so to bring these misclassified points right close to where it belongs, right? That's where the cost penalty comes in. So you see cost penalty as part of your outputs data, right? Okay, so that's what it means, right? So, and same applies to this one, right? To bring it closer to the cluster where it belongs, right? It's a cost penalty associated to that, right? Okay, so that is some of the parameters that you manipulate or change to basically optimize and improve upon their accuracy percentage. If there's the need. Let's say when I did the classification processing, right, and I had a, let's say for fine Gaussian, I had a, let's say 80%, right, or 85%. I'm thinking that 85% is though it is a good accuracy, I can basically improve it upon it, right? So how do I improve upon it? So that is when I increase the cost penalty, right? let's say cost penalties was giving me, let's say 3. I can increase it to 6 so that I can bring it closer to where it's supposed to be, right? Then basically, it will, I can improve upon the accuracy. Okay. Then another way of, also, increasing the training accuracy is selecting the optimizer algorithm for each algorithm. So there is an optimizer button, algorithm for, let's say, for fine tree, fine KNN, fine Gaussian, and for all other, listed algorithms, classified algorithms that is in there drop-down window that you will see. So now let's take a look at the confusion matrix. Okay, so we have a pole to ground fault, right? We have a pole to pole fault, and we have a steady state, right? Okay, so this one is giving me for faulted condition. Right? And this one is giving me for no fault condition. Right? Similarly, these two is giving me for faulted conditions, and this one is giving me for non-fault condition, right? Okay. This vertical axis is my actual data. And the horizontal axis is my predicted data, where what I want to achieve to match my actual data, right? Okay, so as you can see over here, right, for a pole to ground fault, out of the total data for that is 465 plus 18, and this one is total data for pole to pole fault is 471 plus 9, which is 480, right? And for steady state, it's 427, right? Okay, and this one is 465 plus 18, that is 483. Okay, so for pole to ground fault, out of 483 data points, right, 465 data points were predicted correctly as pole to ground fault, and 18 out of 483 were predicted wrongly. Then for pole to pole fault, right, 9 out of pole to pole fault were predicted wrongly as pole to ground fault. Then 471 out of 480 were predicted correctly as pole to pole, right? Pole to pole matching pole to pole, right? And this one, pole to ground, 18 out of 483 were predicted wrongly as pole to pole faults, right? Okay. And for steady state, 0 misclassification. Okay. So for steady state, right, as you can see over here, 0, 0, just like we have over here, right? And 427 out of 427 were classified correctly as steady state no fault condition. Next is basically percentage wise, right? Okay, so the previous slide basically gives us the quantity in numbers, right? Okay, so what it's telling us is, like I told you, this is my actual data, my true class, right? And this is my predicted data, right? Okay, so it's telling me that 96.3% of pole to ground fault were classified correctly. 3.7% were classified wrongly. And basically, there was no misclassification for steady state, right? Okay, so for pole to pole fault, 1.9% were misclassified as pole to ground, and 98.1% was correctly classified, and no misclassification for steady state. Same applies to steady state, right? 100% was correctly classified. No misclassification. So this is another form of confusion matrix, but this time positive predicted value, right? And that corresponds to all these percentages that you are seeing over here based on correct classification, and false discovery rate is just a misclassification, right? For all this, as you can see over here, for all these categories. Now let's take a look at the fine KNN, and we'll take a look at the scatter diagram and the confusion matrix for this. Okay, so for the fine KNN, right, this is the scatter diagram, as you can see over here, right? So this is where the misclassification comes into play. So that is why you are seeing this percentage, overall percentage is below, slightly below 100%, right? It's because of this crossover point over here, where a little bit of misclassification over there. Okay, so for the fine KNN, right? Okay, so what it's telling us is that for a pole to ground fault, right? Similarly, for this is the actual data points, right? This is my predicted data points, right? 98.3% was classified correctly for pole to ground fault. 1.7% of it was misclassified as pole to pole fault, and zero, there was no misclassification for steady state, in between steady state and pole to ground fault. For pole to pole fault, 1.7% was misclassified as pole to ground, and 98.3% was correctly classified as pole to pole fault, and for steady state, 100% classification. Okay, so my next slide shows confusion matrix in a different dimensions, right? Okay, so I have the positive predictive values, similarly to correct classification in between actual and predicted, 98.3%, and false discovery is based on basically misclassification, right? As you can see over here, this one is correct classification and accuracy between basically actual and prediction. Next, it's basically for the fine Gaussian, right? Okay, so this is the scatter diagram, right? Okay, so same thing, total training samples. As you can see over here, this is where the misclassification comes from, right? The crossover from here. You can see some points over here. Okay, so for the confusion matrix for the fine Gaussian, right? Okay, so what it's telling me is I have a total of 483, right? And a total of 450 plus 30, that's 480, right? And 427, right? Okay, so pole to pole fault is 480, pole to ground fault data point is 483, and steady state is 427. So out of for a pole to ground fault, right? Out of that, the whole 483 was correctly classified as pole to ground fault, right? There was no misclassification, between pole to ground fault and pole to pole, and between pole to ground fault and steady state, right? Okay. So for on the other hand, for pole to pole fault, right, 24 of it was misclassified as pole to ground, and 450 data points were correctly classified as pole to pole, and 6 of it was misclassified as steady state no fault condition. For steady state no fault, correct classification 100%. For all 427 data points were correctly classified. Like I told you that, there's a way to, improve upon the accuracy, right? You can improve upon that accuracy by basically introducing, increasing the cost penalty, right? Right, and also selecting the optimization algorithm. So those are the different ways that you can do to improve upon the accuracy. Next is basically percentage wise, right? Okay, so previous slide gives us the quantity in numbers, right? Okay, so it is telling me that for a pole to ground fault, 100% of it was accurately classified as pole to ground fault during training session, and 0 misclassification in between that, and pole to ground and pole to pole, and steady state, right? Okay, for pole to pole, 5% of it was misclassified as pole to ground, and 93.8% was correctly classified, and misclassification between pole to pole and steady state. And for steady state, 100% classification. So this confusion matrix is quite similar to the previous slide, but this time, positive predicted values, right? Similarly to those percentages, as you can see over here, which is based on correct classification, and misclassifications are all these false discovery rate percentages that you see over here. Now let's take a look at the testing classification, right? Remember, I made mention that out of the total data points, right, you can basically set aside 95% for training and 5% for testing, right? So out of the total training points, I set aside 5%, and basically you see the amount of what the 5% first. Okay, so the total testing sample was 73, right? Okay, out of the 1,300 and something for the training, right? Okay, so this is the prediction speed for fine decision tree algorithm, right? And this is for this prediction speed for fine KNN, and this is the prediction speed for fine Gaussian, right? Okay, so the accuracy is this, right? So as you can see over here, right, fine Gaussian is giving me a very high accuracy, lower cost penalty, and higher, prediction speed, right? But the caveat on the drawback is that during the training session, right, it was giving me a longer training time, and I told you that the training time corresponds to higher computation burden and basically cost, right, and basically compromising performance. So those are some of the factors that you want to look at. So basically, I will rather basically look at lower training time, right, which basically translates into lower costs, right, lower computational burden, right, and basically quite close, higher accuracy, right, as you can see over here, right, and my prediction speed, basically select between 6,000 and this. So basically, your best classifier is between this and this, not this one, because the training time is too long. Right? Okay, so out of that, basically I have a total of 24 plus 1 for pole to ground fault, 25 plus 1, 26, and 22, right, for steady state data points, right? These are the data points that I have for steady state, and 26 are data points for pole to pole, and 25 data points for pole to ground, right? Okay, so out of that, right, 24 out of 25 basically was accurately tested and gave basically the correct prediction, from the actual to the prediction, and one was misclassified, right? Okay, for the pole to pole fault, one was misclassified and 25 was accurately classified. And for steady state, all of them were correctly classified. Next is percentage wise, right? Okay, so the previous slide was quantity numbers, and basically we'll talk about the percentage wise. Okay, so this is my actual, this is my predicted, right? Okay, so 96% of the pole to ground fault was basically predicted accurately, and 4% was mispredicted or misclassified. Then for the pole to pole fault, 3.8% was misclassified, and 96% 0.2% was correctly classified. There was no misclassification between the pole to pole fault and steady state. And for the steady state, basically 100% classification. So similar confusion matrix and same percentages just like in the previous two slides. Now let's take a look at the testing classification for the fine KNN. Okay, so for the fine KNN, similarly, 24 out of 25 was correctly classified as pole to ground fault out of the pole to ground fault data points, and for pole to pole fault, one of them was misclassified as pole to ground, and 25 of it was correctly classified as pole to pole, and zero misclassification between pole to pole and steady state. And for pole to ground, one of it out of 1 out of 25 was misclassified as pole to pole fault. And steady state, all of them were correctly classified. Next is basically percentage wise. Okay, so pole to ground fault, I have 96% correct classification, 4% misclassification between pole to ground fault and pole to pole fault, and 0 misclassification between pole to ground fault and steady state. Then pole to pole fault, I have 3.8% misclassification between that and pole to ground, and correct classification pole to pole and pole to pole was 96.2%. Then misclassification between pole to pole and steady state is 0, and 100% correct classification for steady state. Similar percentage wise from the previous slide, you know, and all these are all shown in the previous slide. Now let's take a look at the testing classification for the fine Gaussian support vector machine. Okay, so for the fine Gaussian, right, out of the testing sample, right, of 73, right? Okay, so that is everything in this box totals 73, right? Okay, so pole to ground fault, 25 of them was correctly classified, no misclassification, 0, 0. And for pole to pole fault, 1 was misclassified as a pole to ground fault, 25 was correctly classified as a pole to, no misclassification between pole to pole and steady state. And steady state, 22, all of it correct, accurate classification, right? Okay, so like I indicated, you know, basically you have to look at, as you can see over here, fine Gaussian, though it says the prediction speed is high, but the caveat is the training data, it's basically too long. It takes too long a time to train the data, right? So, and that's cost. Okay, so percentage wise, 100% pole to ground fault classification accurately, then 0, 0, and pole to pole fault 3.8, and in between pole to pole and pole to pole is 96.2. Then steady state no fault is 100%. Then another, you know, confusion matrix in different form, right? And positive predicted values, right? This is basically what it's telling you is a correct classification after training, right? After testing, right? Okay, so testing 73, these are all the percentages that I obtained, and only misclassification was 3.8% for between pole to ground faults, for pole to ground faults, right? Okay, and this one is 0 and 0.